To close this section, we're going to work through a full example of what a memory system might look like. This will be a fairly small virtual memory system, but one that should serve as a good example of what goes on in real systems. All right, so here's our very simple memory system. We're going to have a 14-bit virtual address and a 12-bit physical address. Not all that many bits, but you get the idea. Just think about replacing that with 32 and 64 for the virtual address. The page size in this case is going to be 64 bytes, also a very tiny page size, not what we typically see. It would be more something on the order of 8 kilobytes, for example. So if we have these values, then here is our 14-bit virtual address, and here's our 12-bit physical address. Given that we have a 64-byte page size, our virtual page offset will be 6 bits, as will be our physical page offset, because those pages are exactly the same size. The remaining bits are the virtual page number and the physical page number, 8 and 6 bits respectively. The page table for this system is going to have 3 columns: a virtual page number, the corresponding physical page number, and then a valid bit signifying whether that particular entry is valid or not. Here on this diagram, I'm only showing the first 16 entries. Of course, there would be 256 total entries for the page table because our VPN, our virtual page number, is 8 bits. So we would have 2 to the 8 entries in our page table, or 256. Now, you can see that if we had a much larger virtual address space, the number of page table entries could be huge. And in fact, that's a whole nother discussion of what do we do when we have very, very large page tables that we couldn't actually even fit in memory, in the physical memory. So we'll defer that discussion, however. For now, though, keep in mind that this is only 16 out of 256, so that there's many more entries going all the way to FF for our virtual address, for our virtual page number. Okay, our TLB for this simple memory system is going to be 4-way associative. That's actually pretty typical for TLBs. We want to have some flexibility of how we can store these page table entries in the cache, so we do not use direct map caches typically for TLB. And in this case, there's only 16 entries. This is also a very, very tiny TLB. A more typical number would have been 256 or maybe 1K of entries. But again, here we only have 16 and 4-way set associative, meaning that there's 4 entries per set. That means we'll be using 2 bits for our set index in our cache, and the remaining bits, in this case, the remaining 6 bits of the virtual page number for the tag. And you notice that we're only using the bits of the virtual page number for this TLB because the virtual page offset will not enter into things. We're not translating that. We're not looking anything up for that. That just goes straight down to the physical page number. So the TLB only needs to cache the virtual page numbers and their corresponding physical page number. So here at the bottom, you then see typical contents for this TLB. It has these 4 sets, 4 entries per set, for a total of 16, some of which are valid, some are invalid, and for the ones that are valid, we have a corresponding physical page number. Okay, and of course the tag to check the high order 6 bits of the virtual page number to also make sure it is the same as the one we're trying to access, just like any basic cache would do. The last part of our sample example system is the system cache, the main memory to CPU cache. And in this case, this will be using physical addresses. So we'll be taking our physical address and breaking it up into the bits we need for these cache accesses. There will be a block offset of only 2 bits because we're going to use a block size of 4 bytes. Okay, so we only need 2 bits to index into that block. We will then have 4 bits for the set index, and that's because this particular cache only has a total of 16 lines, and it's direct mapped. That means that the remaining part of the physical address, those last 6 high-order bits, will be the tag component. And here you see some sample contents for that cache, and here we're showing the entire cache as well. Okay, so when we put all of those together, here's our system cache, here's our TLB, and here is the first 16 entries of our page table. Remember, the page table has a total of 256 entries, only showing 16 here. Now, you might want to save this page and have it open in another window as we do some example address translations using the data that we've put into these tables and caches shown on this slide. So keep this one around, have it open in another window. All right, so let's take a look at our first example. We're going to go to the address 03D4 in hex and see what happens. First, we need to map it to a physical address and then access our cache. So how do we do that? Well, let's take that virtual address and break it up into its components. Okay, the low order 6 bits are that offset, that virtual page offset. The high order 8 bits are the virtual page number. Those bits are further divided into the TLB index and the TLB tag. And you can see in this case that our TLB index is 3 and our TLB tag is 03. So that's what that first part of our construct will be. Now, is this a TLB hit or not? Well, if we go to that particular set in the TLB and look for that tag, if that tag is present, we would like to know if that's a valid entry or not. And we'll see that, in fact, if we refer back to our TLB contents, that is a hit, and it is not a page fault because that is a valid entry. So let's take a look at that real quick. And you'll notice that in set 3 here, we have the tag 03, and in fact there is a valid bit. So that's why that worked out. We can now pick out the physical page number as being 0D. That is now our physical page number. Okay. Now that we have everything we need to put our physical address together. And here it is. Here's the 0D. Okay, and then of course we're just moving the virtual page offset down to the physical page offset. We can now break things up into our components for the system cache, and we see here that those correspond to 0 block offset index into set 5 and the tag of 0D. Okay. Now that's purely coincidental in this case, that the tag is the same as the physical page number. That's just the way this number of bits for each of the components worked out, but that would not be what would happen in every case. Now, is this a hit? Well, let's go look at the cache that we have, and whether in set 5 we have a valid entry with the tag 0D. And what we'll see is that in fact we do. And then we want the particular byte at offset 0, and that byte is the byte 36. Okay? And you should make sure to verify that on that example page that I asked you to save earlier. All right, let's do another example. In this case, the address 0B8F, And you can see here we've already broken it down to our TLB index and TLB tag. And of course we go and look at this and it's not in the TLB, so we have a TLB miss, and that means that we don't know what to do at this point. We don't have our table entry, our page table entry, so we don't even know if this page is in memory or not, hence the question mark here. And we, of course, don't have any handle on a physical page number. So what we're going to have to do is go and read that page table entry, bring it into the TLB cache to resolve this. Okay, and until we do that, we really can't go any further. Let's take a look at a third example, this time the address 0020 hex. And again here we're looking at a TLB index of 0 and a TLB tag of 00. If we go look in the TLB, we'll see that this is also a TLB miss. The valid bit is set to 0 for this particular entry. But unlike the previous example, we have the page table to go look things up in. So if we take care of that and access the page table for this first page table entry, namely the one starting for virtual page number 0, we go there and we see that in fact it's not a page fault. The page is in memory. We just didn't happen to have it cached in the TLB, and that page number, the physical page number corresponding to this, is 28 hex. So that gives us enough to put together our physical address. Here's our 2 and 8 from the page table entry, and the physical page offset carried down. And then if we go to our cache and look at the set 8 with the tag 28, we'll see that in fact we have a miss, and we're going to have to go to memory to read that location. So this is a case where we got a TLB miss, but we were able to read the page table entry quickly. We had that available, and once we got the physical address, we now have a miss in the cache and have to go and bring that in from memory. Okay, so those are a few examples, and there's many more available in the text and so on. I encourage you to take a look at that. To summarize this section, the programmer's view of virtual memory is that each process has its own private linear address space that cannot be corrupted by other processes, although we might be sharing some parts of it with other processes, mostly read-only sections like library code, for example. The system's view of virtual memory is that we're using memory efficiently by caching virtual memory pages. So we're making good use of that small physical memory that we have. And it's efficient only because locality works. Remember, when we're accessing one part of memory, we're likely to access other parts of memory nearby. This level of indirection that we use to implement virtual memory simplifies memory management and sharing, and provides a good way for providing for protection by interpositioning this place to check permissions. By looking at the page table entries and seeing which bits are set, how we can access these different memory pages. Okay, so to complete the summary of our memory systems, we have L1 and L2 memory caches. These are purely a speed-up technique for main memory to CPU. It's totally invisible to the application programmer and even to the operating system for the most part. It's implemented completely in hardware. That's how processors are designed, to support these caches directly. Virtual memory, on the other hand, needs the operating system to step in. It needs the operating system to create and kill processes, switch between processes, to help it with protection, and also to help it with getting pages from disk and bringing it into physical memory. The software that is involved in the virtual memory system allocates and shares these pieces of physical memory among the processes. It has to maintain these page table entries and how they should be shared, and has to handle exceptions, how to find victim pages and a replacement algorithm for determining the best way to allocate that small physical memory to best handle the needs of these large virtual memory spaces. And this is all done through hardware-defined mapping tables that are made to be as fast as possible because, of course, we need to use them for every memory access. So that hardware is really critical to making virtual memory practical. And we do a lot of acceleration of that process. An example of that is the translation look-aside buffer, a super specialized little cache just to aid with the virtual memory address translation problem.